today, the title of my lecture will be Generative AI, especially Variational Autoencoder. Especially, this generative AI model is very suitable for image generations. At the beginning of my class, I'm going to introduce the basic architecture of variational autoencoder, and probably at the end of this class and next class, I'm going to derive some equations to talk about the loss functions. Before starting to talk about the variational autoencoder architecture, let's review architecture of GAN. In the previous class, we was talking about the architecture and loss function of a generative adversarial network. It has latent vector, it has generator network, and model parameter is assigned as theta g. Of course, during the training process, we have to find optimal theta g. Of course, this generator network is made of kind of convolutional neural network. There is a kind of deep neural network. Output of this generator network was X real, X fake. That is becoming to the input of discriminator network. And model parameter is represented by theta d. Of course, this discriminator network is also has a form of convolutional neural network. It is a kind of deep neural network. Another input to the discriminator network is X real. For example, if we want to train this generator so that this generator output as fake is as similar as X real. Let's assume this X real is Picasso pictures. We want to train generator so that it can make an output X fake, which is very close to X real, so that discriminator network cannot distinguish whether it is X fake or X real. So output of discriminator network is Y. Usually it is between 0 to 1. If output is 1, discriminator feel like this fake image is real. If output is 0, discriminator network think this fake image is a fake. So during the training process, generator network and discriminator network is fighting each other so that generator make the best fake image and discriminator network wanna distinguish it as a fake. During the training process, we want to train generator and discriminator so that this loss function becomes minimal. You remember this function is object function of the training of generative adversary network. First, we are trying to train discriminator. Of course, the model parameter is theta d, so that x real output of discriminator network with x real input is becoming 1. Because this is log function, discriminator network output, if that is becoming 1, then this whole function becomes minimal. The first term means that this discriminator output y should be equal to 1 when its input is real. That is the basic function of discriminator. If the input is real input, Picasso picture, output should be equal to 1. We have to train discriminator network so that it knows that what is real. That is the first term. And mathematically, because this is log function, if the fd is equal to 1, it's gonna have I'm a little bit confused. Oh, min-max. Okay, so this is the maximal point. We have to train discriminator so that this term is becoming maximal. That is the point here where discriminator output is equal to 1. There is another term in the objective function here. Generator output is actually a fake. And to minimize this term by having generator network, that does means that to minimize this one, this is a kind of, I remember, when this output is equal to 1, this whole term becomes minimal. Because this is log function. To minimize this whole function, we have to make fd is equal to 1. That means we have to generate generator network so that discriminator doesn't know whether it is real or fake, but it assumes it is real. Then its output is becoming 1, and 1 minus 1 is becoming minimal. So my point here is that by training there are two parts, training discriminator and training generator. We are trying to train generator so that discriminator output is becoming 1. So discriminator cannot distinguish whether it is fake or real. Then output is becoming 1 minus 1, that is nearly close to 0. Then log 0 means minus infinite. That is the requirement of minimal objective function. That is the basic. So far, this was the explanation of this generative advisory network architecture and loss function. Now, let's start with VAE, Variational Autoencoder. Variational autoencoder has two parts. First one is encoder. Generative advisory network has two deep neural network. One is generator network, the other one is discriminator network. Meanwhile, variational autoencoder has two parts. First one is encoder. Second part is decoder. Of course, we can use CNN type deep neural network to build up the encoder and decoder. Let's assume your input is a picture, image xi. I is the index to represent different pictures, different images used for training process. Output is gonna have image as well. Output image is represented by pi. Dimension of pi could be d by d. Between encoder and decoder, we have G space. We have latent space. Output of encoder will have mu I and sigma I, and the size of this vector is J. What does this mean is that in the G space, if we have an input and output of decoder we are assuming that it has some Gaussian distribution. It's very interesting. And in the G space, we believe that if we plot one, two, three, four, five, six, seven, we may have G values, latent vector value. Some of them may be number 1, some of them value may be number 2, some of them may be number 4, 5, 6, 7. It may have certain distributions and probably density probability density distribution. Somehow it may have average and it may have variance. This is very basic concept of variational autoencoder and diffusion models, which we will talk about this week and next week. Depending on images x1, x2, x3, we may have different distributions. Let's assume this one is tiger, this may be a cat, or this may be a lion. Basic philosophy hidden inside variational autoencoder is that in the G space, if we convert each images into G space, each image may have different Gaussian distributions. Different Gaussian distribution means different average and different variance. In real world, in human world, Joungho, Junhyun, each has symbolic representations. If I say him, he is Joungho, I don't know what does that mean. Just we human made a symbolic representations. But to explain who is Joungho, we may need a whole book. He is 180 centimeters tall. He has a new girlfriend or in an old relationship, and he has to be happy. And maybe we may need a whole book. But symbolically, in human language, we are using Joungho or some name, tiger, lions, something like that. But somehow, in generative AI society, each person or each image may have certain distributions. Especially we assume it is a Gaussian distribution. And one day I was asking to myself, why it is Gaussian? Probably Gaussian function is very easy to handle mathematically. There are many ways of doing the addition, multiplications, and time delay. And mathematically, somehow it is an exponential function. It is easy to do many mathematical manipulations. But anyway, basic understanding of variational autoencoder is that in the G space, each image can be represented by a Gaussian function. This is one-dimensional Gaussian functions, but we can have n-dimensional Gaussian function. In the two-dimensional, it may be some area. Three-dimensional case, it is maybe some volume. So in space, we have Earth, Moon, Sun. Somehow, around Earth, we may have oxygen and hydrogen. Maybe a gas distribution could be a Gaussian. So very unique feature of this variational autoencoder is that in the G space, it is Gaussian distribution. So one day I was wondering, why do we need encoder and decoder? We may directly transfer images to output images, but somehow it has encoder and decoder architecture. In the middle, we have G-space. What I learned is that after training, if we want to generate the new images, let's assume that we have tiger distribution and we have cat distribution. And we want to generate a new image, which is 50% tiger, 50% cat. How do they do that? They are choosing this area, where in the G-space, it has an overlap between tiger and cat. And by choosing this G-space in the middle, if we operate generator, we can generate new images. Somehow, manipulation or creation of generation of new images can be done easily in the G-space. So that's why we have G-space between encoder and decoder. And because in the G-space, each identity has Gaussian distribution, we can do some manipulations using the Gaussian function. It can be easily done. I know it is a little bit weird, but nobody explained to me. I developed my own philosophy to understand this variational autoencoder. So now, output of DNN, deep neural network output, Q pi is an encoder. Input is real image. Output is average and variance. So this deep neural net encoder produces who is average value and who is variance for each images. But let's assume that we have mu and variance, but here we want to generate latent vector. I is an image I, and we may have GI1, GI2, GI3, and GIL. So our idea is that this variational autoencoder is multiplied by epsilon. Epsilon is a standard normal distribution. Average is equal to 0. Variance is equal to 1. Then we can sample this set of latent vector. Maybe this might be GI1, this might be GI2, and GIL. Because we know average and variance, by multiplying it with standard normal distribution, we can generate actual distributions. But there might be millions of latent values. We randomly sample those numbers to construct latent vector. And then what are doing the decoder? Decoder transform this latent vector GI1 to GIL to image conversion. let me explain this generative variational autoencoder one more time. Variational autoencoder has two deep neural networks. First one is encoder, second one is decoder. Between the encoder and decoder, we have latent vector. So function of encoder is to transform input images to latent vector. Decoder function is to convert latent vector to real image, PI. Later on, I will tell you that by comparing XI to XP, we want to make it as close as possible. There might be many different ways of loss function to distinguish input Xi and output Pi. One of them is mean square error. Second one is entropy or KL divergence. We can use that kind of loss function. And we are trying to, this encoder-decoder architecture is trying to reproduce Pi as close as Xi. Then let's assume this variational autoencoder is very well trained. Then when we are trying to generate new images, we are doing operation in the G space. By using the G space, mathematically it is easier to handle compared to manipulation in the image space. That is the secrecy of this variational autoencoder. Of course, this encoder is deep neural network. Usually it is a kind of CNN network to convert images to vector space, and generator is a transformer from vector space to image space. It's a kind of CNN neural network. Second observation or philosophy hidden in this network is that we have philosophy that each image has certain Gaussian distributions. There might be eye color or body color or tail shape, ear. Maybe there might be many different types of probability density distributions. It could be color or tail, leg or ear. There might be many different ways of probability distribution functions. In the G space, we can make this kind of vectors, and each vector has some numbers, and the number of this identity may have Gaussian distributions. In the G space, for each image, we have G1, G2, G3, and it may have certain numbers. 3, 1, 4, 6, 2, 1, 5, 6, something like some of numbers distributions. If we convert them to probability density distribution with different numbers, we may have certain Gaussian function. So if we accept that philosophy, encoder output has to define the average and variance of Gaussian distribution. And in order to convert this average and variance into real data of set, we are doing sampling. How to do that? We are multiplying it with standard normal distribution. By doing that, we can randomly sample some numbers. That set of that becomes a latent vector. And the generator network is actually to convert this G-space vector to real images. So when you are trying to, let's assume that you have latent vector 1, latent vector 2, latent vector 3. By having that, by doing some numerical manipulations, you can generate new image. Now I would like to talk about the loss function. First loss function is to compare input image and decoder output. Mathematically, it is cross entropy. That is represented by this function log in the Wednesday class. I'm going to spend some time to derive all these equations rigorously. But at this moment, let's accept that. What does that mean is that let's assume that we have latent vector 1 and we have output of latent, let's assume we have latent vector 1 and output is the output is the generator output with the given latent vector G, and then that is becoming now we have Xi. So entropy of this output is this one. This has to be minimized. You remember that this is log function. You want to make this log function as small as possible in entropy world. You remember that in order to have good output of AI, we want to output entropy should be minimal. That is a kind of condition to distinguish whether it is real or fake. We have to have minus sign here. So one objective function of this variational autoencoder is, what I mean is that entropy of this output should be minimized. Second, this is called reconstruction error. Second loss function is on here. we have two loss function. First one is reconstruction error. Second one is regulation error. What does regulation error means is that this output of encoder has to be Gaussian function, and average summation of average and variance should be as small as possible. What is this condition means? Mu is equal to 0 and sigma is equal to 1. That is the condition of minimal reconstruction error. What does that mean is that they are training encoder so that output of this average and variance should be as close as possible to standard normal distribution. Standard normal distribution means that average is equal to 0 and variance is equal to 1. So if you have arrow, this is xi, if this is encoder, output should be somewhere in the middle in the Gaussian distribution. That enforcement is represented by this regulation error. On Wednesday class, I'm going to spend some minutes to derive this reconstruction error term and regulation error terms. At this moment, let's only talk about the meaning of these two equations. The first, loss function. You remember that in the generative adversarial network, we had two loss functions. One is for generator network, and the other one is for training discriminator network. Here we have two loss functions. One is to control the output, especially for decoder, and we want to train decoder so that entropy of output has to be minimal. And second one is for training the decoder, and we are assuming that because in the G space we have Gaussian distribution, we want to train the encoder so that it is becoming a standard normal distribution as much as possible. This is the end of today's class, and on Wednesday I'm going to come back again and explain it again with rigorous derivation of these equations. Thank you for your patience and attention. And I feel a little bit sorry to you that because diffusion model is much more difficult to explain. And reinforcement learning is very straightforward, very easy to understand and to explain. Let's be patient and let's talk about that on Wednesday. Thank you.